Okay, so this video lesson is called What are Ions? And up to this point, you guys have been introduced to ions and been shown some things regarding ions, but we're going to really get into what they are and kind of get a good foundation for how this ties into all the things that we have been talking about in regards to the periodic table. So what I've done over here to the right is you can see there are two major bond types when it comes to atoms coming together to get stable. There's two major bond types. There is ionic bonding right up here up top, and then there is covalent bonding, which you see down here in the lower right. Right. So the difference is that in ionic bonding, you have a loser and a gainer. You have atoms that lose valence electrons, and you have atoms that gain valence electrons that come together, and they end up having these opposite charges, okay? So you've got some positive charges here, and then you've got some negative charges. So today we are going to really talk about how these negative and positive charges develop. Like, ions are technically, so these positively and negatively charged particles, these atoms, are charged because they have lost or gained electrons. And because they are oppositely charged, remember opposites are attracted, it creates this really strong electrostatic bond known as ionic bonding. So a lot of solids are held together by ionic bonding. So like all types of solid forms of matter are held together by ionic bonds. So when we think about different types of alloys and like different salts, even some sort of powders or crystals, they are held together by ionic bonding, okay? Now, covalent bonding is different. Covalent bonding, you notice how there's no charges right here, okay? So these are known as molecules, okay? This right here is known as a lattice structure made out of ions, okay? I'm going a little bit more than y'all need to know for this particular chapter, but it's really going to help to kind of make sure y'all keep these straight in the future. So ionic bonding happens between metals and nonmetals that lose and gain valence electrons. It's a complementary, hey, I don't need these electrons, you need them. And then in covalent bonding, they are actually sharing valence electrons, okay? So there are no charges because they don't technically lose or gain. So we're going to talk about these charges today in ions, and then also talk a little bit more about ionic electron configuration as well. So keep in mind, ionic bonding is just one type of bond, but covalent bonding is a separate type of bond where what they're doing fundamentally with the valence electrons is different. There is sharing going on, okay? So we're going to focus on the formation of these ions, these charged particles today. Okay, so one of the things that we've talked about in this particular chapter in terms of periodic trains is ionic radius. Okay, so the radius is the distance from the nucleus to the outer valence shell in an atom. So all the atoms on the table, even these ones that are blacked out right now on this table, all the atoms have a particular size, like atomic radius. Now, an ionic radius is the radius once an atom has lost or gained valence electrons. So those ions I just was talking about, those charged atoms, have a ionic radius once they have lost or gained valence electrons. So let's kind of review a few of those things. First of all, groups 1, 2, and 13 have 1, 2, 3 valence electrons, and they lose those in order to become stable. They lose their valence electrons. It just makes more sense because they need 8. The octet rule says that atoms will work to achieve 8 valence electrons. They will either lose, gain, or share in order to try to get that 8 to be chemically stable. Well, we know that the elements of group 18 are already stable. So that's going to be your noble gases. They already have a full valence. They either have 8, except for helium. Helium has 2, but that first shell only needs 2, so it's stable as well, okay? So you've got groups 1, 2, and 3 that like to lose in order to become stable. And then you've got the elements of groups 15, 16, and 17 that have 5, 6, 7 valence electrons, and they gain in order to become stable, okay? Because they've got 5, all they need is like 3, 2, or 1 more, okay? So they've already got over halfway what they need to be stable, okay? Now, when we talk about ionic radius, this was something that's already talked about in the periodic trends, is if you are an element that has 1, 2, or 3 valence electrons and you lose your valence electrons to become stable, then, oh, I meant to, I'm not sure. All right, you actually become smaller, all right, as an ion, okay? And that is because they lose an energy shell, okay? So groups 1, 2, and 13, they actually are larger as a regular ground state atom, but as an ion, they are smaller, okay? So their ionic radius is smaller than their original atomic radius. Now, the elements over here in group 15, 16, and 17, they get larger because, not because they grow a shell, but because when they take in those extra electrons, like charges, negative, 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 they all were going to repel and push away from each other, which ends up making expansion occur in the shell. So they have a larger ionic radius due to increased electron repulsion, and that's groups 15, 16, and 17, okay? These over here get smaller due to the loss of an energy shell. So keep those in mind. Like, that is, you've got 18 groups on the table, and I'm telling you 6 that you need to know what they do, all right? Now, group 14. So I'm going to take a look at these guys for just a second, all right? But group 14, all right, you know how I was showing you those covalent bonds where there's molecules and there are no charges? Group 14 sticks to covalent bonding. Now, they're not the only ones. All the other nonmetals over here will actually share as well, as long as it's with another nonmetal. Okay, but that's more to come on that, okay? But for right now, do know that groups 15, 16, and 17, when it comes to ionic bonding, that is losing and gaining, they are the gainers, and then these are the ones that lose, okay? Metals lose, non-metals gain in ionic bonding, okay? So y'all should be putting that together, because that's something that we have talked about, is that these over here, the metals, make up most of the table over here, okay? And you can see they're the ones that are losing valence electrons. And another thing you should be putting together is that the nonmetals are the ones that are gaining, okay? So keep that in mind, okay? Because that's something that is kind of needs to be understood, even though it's not mentioned. These are our metals, they always have been. These are our nonmetals, all right? And then the metalloids, they get kind of mixed in, and they can do kind of either or, right? Because they are metalloids. All right, what we're looking at and what we're going to focus on that I haven't really explained to you guys is the charges, okay? So up here, you can see that there are these charges, all right, that are associated with certain groups. So notice how those that have 1 valence electron, 2 valence electrons, or 3 valence electrons have positive charges. That is not a plus sign, okay? It's not an addition sign, because a lot of students are like, well, they lose, so why isn't there a minus sign? Well, those are not minus or plus, addition and subtraction signs. And that's not what they are, okay? They are charges, letting you know if that atom, if that ion has a surplus of protons that are positive or surplus of electrons that are negative. And we're going to see that on the next image that I share with you guys, all right? Now, over here, you can see that the ones that gain valence electrons, okay, so those that have 5, 6, 7 valence electrons and gain, they have charges associated with them that are negative. 3 negative, 2 negative, 1 negative, all right? So that's important. At the very least, you need to remember this. You need to remember that, hey, it's 1, 2, skip the middle, 3, 4, 5, 6, 7, 8 valence electrons. We've talked about that pattern across the group. And you also need to remember that group 1 as an ion has a 1 positive charge. Group 2 as an ion has a 2 positive ionic charge. Group 13 has a 3 positive ionic charge. There is no charge on these elements because they share. And like I said earlier, they don't get involved in ionic bonding and become ions. An ion is a charged atom, okay? Meaning it's either positively charged, which are going to be those right here that lose valence electrons, or it's going to be negatively charged, which are going to be these groups right here that gain valence electrons. So let's look at this and put it together with some stuff we already know. Okay, so this is the table or chart that I provided online digitally for you guys to use today, and it's also what I provided in class for students yesterday and today. So we're going to focus on the elements of the S and P sublevel block. We have talked about these elements before. These are called the main group elements, okay? So the elements that are in the S block are the elements in groups 1 and 2, and then the elements that are in groups 13 through 18, that's the P blocks on the periodic table, all right? So when we've talked about the valence electron count already, it goes 1, 2, 3, 4, 5, 6, 7, 8, all right? So we skip the D sublevel block. Group 1 has 1 valence electron, group 2 has 2, group 13 has 3, so forth and so on, okay? At this point, these are things you should know. Now, other things that have also still been mentioned is, all right, if you've got 3 or less valence electrons, in order to become stable, you lose your valence electrons, okay? So stability is achieved how in ionic bonding? They lose, okay? So we're talking about when in ionic type bonding, when becoming an ion, what do? Groups 1, 2, and 13 will lose their valence electrons because they have 3 or less. Now, groups 5, 6, or 15, 16, 17 that have 5, 6, 7 valence electrons, they gain in order to become stable. All right, now, in the last 3 columns, we are going to use a sample element, okay? So keep that in mind. This is just an example. So this is an element from group 1. This is an element from group 2. This is an element sulfur from group 16, okay? We're going to use it to establish those charges. So those charges I just showed you, that's like 1 positive, 2 positive, we're going to make sense of why they are there, like what they come from, okay? So if we take a look at sodium, all right, it says proton versus electron count once stable. So sodium is number 11, atomic number 11 on the periodic table. So that means it has 11 protons, okay? That's 11 positive protons in the nucleus. Now, before it bonds, it also has 11 electrons. However, and normally what happens is these cancel each other out. 11 positive charges cancels out 11 negative charge, so the atom is neutral, right? However, whenever it loses, an atom loses or gains, this changes. So sodium has 11 protons forever and always because proton count doesn't change. But right here, it loses that 1 valence electron. So now it has 10 electrons total, no longer 11. Now, what happens is you now have, and I just messed it up. Sorry, that's supposed to be a negative charge. I apologize. So it has now 11 positive charges and 10 negative charges. So now it no longer all cancels out. The 10 negative charges are canceled out by 10 positive charges, but you have an extra proton left over. All right, so basically that's saying sodium has 3, 4, 5, 6, 7, 8, 9, 10, 11 protons total in the nucleus, and then 11 total electrons in the electron cloud. Well, in order to have a full valence, in order to have 8 valence electrons, sodium loses this to become stable. So what ends up happening is you've got these canceling each other out, and sodium has an extra positive charge, an extra proton number compared to its electrons. So this is not a plus sign, okay? That is just saying, hey, sodium has an excess proton now. So it's now got a 1 positive charge. So consequently, when we look at the other elements that lose electrons, okay? So if we go down to magnesium that has 12 protons, and it originally has 12 electrons. However, that electron count goes down because it loses 2. So now, after it loses its valence electrons, magnesium has a total of only 10 electrons. So now, magnesium has a surplus of 2 positive charges. And so this is what happens also with aluminum. Aluminum's got 13 protons. and 13 electrons. But once it becomes stable and becomes an ion, it loses 3 electrons. So now it's got a 3 positive charge. So that, just think 3 protons. That's what it means. I have 3 extra positive charges and not enough negative charges to cancel them out. So that's where these charges come from. Now, for the elements of group 14, they share. They do not give them away. They don't mess with their electron count. They just share. They don't lose them or bring new ones in. So for sodium, for example, not sodium. Okay, so I don't know really what happened to my screen. Had to redraw it all, but anyway, it's back now. All right. So I was at silicon. So basically silicon is in group 14 and they are a sharing group. So silicon has 14 protons and 14 electrons, okay? It's got 4 valence electrons, but it does not give them away. It does not add to them. So when it shares, it still has its same quantity of electrons. So it has no ionic charge, okay? It has no ionic charge. And I can even jump down here to the sample element argon. Argon has 18 protons and 18 electrons. It does not lose or gain or even share because it's already stable. So you can see it has a 0 charge. It has no ionic charge because it does not, that electron count doesn't fluctuate. Now, when we go to the gainers, all right, we're going to see something different. So the one thing that will never change, and this has been said since the beginning of the year, is the proton count, all right? So the electron count's either going down or up, all right? So as we look at the elements in groups 15, 16, and 17, phosphorus has 15 protons. It gains. How many does it gain? So everybody's like, how many does it gain? It gains 3, right? The octet rule says that you need 8 valence electrons, unless you just have one shell. You need 8 valence electrons to be stable, all right? So for the gainers, they're trying to get to 8, all right? So phosphorus has 5. It needs 3 more. 5 plus 3 is 8. So it now has 18 negative charges. So now what we're seeing is an excess number of electrons. So the 15 positive charges are canceled out by 15 of the negative charges, but now there's extra negative charges, 3 of them, because it gains 3 valence electrons. For sulfur, it's got 16 protons. It has 16 electrons, but once it becomes stable, all right, it gains 2 to have 8. So now it's got 18 negative charges. So it's got a surplus of 2 negative charges. For group 17, group 17, if we're going to talk about chlorine, chlorine has 17 positive charges. It gains 1 valence electrons to have 18, all right, and so it has an excess negative charge of 1, okay? So this is where the charges come from. It is literally what happened. You got protons and equal electrons. Did you lose electrons? And now the protons are on top, so you got positive charges, are you a loser? Or if you have your equal protons and electrons and they gain, now there's a surplus of negative electrons, and so now it has a negative charge. All right, so that is how ions are formed, and then together the positive and negative ions stick together like glue and create an ionic bond. Okay, so lastly, I want to go over this ionic electron configuration business, because this was something that some students struggled with when I talked about it the week before last. So we'll go over it again. So if we're talking about the atoms or the element sodium, sodium is, its original electron configuration is 1s2, 2s2, 2p6, 3s1, okay? Now, what you need to understand, and something that was like fundamental to electron configuration, is know this is energy level 1, this is energy level 2, this is energy level 3, okay? And then there's sub-levels, like especially here in energy level 2. This is your valence shell, okay? You see this exponent 1? That's that valence electron, okay? So we can see it in the electron configuration that the 3s1, let me just get rid of this. that one valence electron in energy level 3, specifically 3s, that's the valence electron that it loses as an ion. So when we write sodium as an ion, and yes, you have to write that positive charge with it now, it is now going to look like this: 1s2, 2s2, 2p6. All right, so this is basically gone. This one valence electron has left, so now we've only got 2 plus 4 plus 6, 10 electrons. So there you go. You can see that once an element becomes stable and loses or gains electrons, that new electron count has to be represented in the ionic electron configuration. So this is what we're looking for when we say ionic electron configuration. This is the ionic electron configuration, okay? I'm just showing the ground state electron configuration up here so you guys can see the difference. All right, so I do another one. Magnesium is 1s2, 2s2, 2p6, 3s2. There's those 2 valence electrons that gets lost, okay? So magnesium 2 positive is 1s2, 2s2, 2p6 now. Now, is it a coincidence that their ionic electron configurations look the same? No, because every time an element loses or gains electrons to become stable and gets this new ionic electron configuration, it should look like a noble gases. So 2 plus 2 plus 6, that's 10. That's neon, which is a noble gas's electron configuration. Same thing here. All right. All right, so I went ahead and drew aluminums for you, went ahead and did this. Look, so here's aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. I want to show the slight difference here. So aluminum's energy level 3, its outer valence shell actually has 2 sublevels in it. So you need to keep in mind it's these two sets of exponents, 2 plus 1, that's the 3 valence electrons that aluminum has. So you should notice in the ionic electron configuration that the entire energy shell 3 is gone because all 3 valence electrons are gone. So this is your new ionic electron configuration for aluminum, the ion aluminum. Okay, so I went ahead and drew phosphorus's. Okay, so here is phosphorus's ground state electron configuration. 2 plus 2 is 4 plus 6 is 10, 12, 15 electrons. There is 15 protons and 15 electrons in a ground state phosphorus atom. But this is the ion phosphorus. It has gained 3 more added to the 5. So it's got 3 more valence electrons. So we're going to add 3. So here's what you need to understand. Here's energy level 3. There's the valence shell. This entire thing is energy level 3. There's the 5, 2 plus 3. That's the 5 valence electrons. It needs 3 more because that's what's going to fill up the p sublevel. All right, so here we go. You've got now 18 total electrons, and you've got 8 valence electrons there in the outer shell. So you can see the opposite with the gainers is that you're actually adding to the electron configuration because you are gaining electrons, okay? And furthermore, we see this happen with sulfur as well as chlorine. So this is sulfur's original ground state electron configuration. It is the 3p4 element on the periodic table. There you can see the 16 original electrons that now are 18 total in the ionic electron configuration. 2 have been added, and so now it's chemically stable. Chlorine, 3s2, 3p5. It needs 1 more here to have 8 total in energy level 3 in its outer shell, and so you see that in the chlorine ion. All right, so that negative charge that you see with these gainers is the addition of electrons in the electron cloud, and we can see that represented in the ionic electron configuration. Up here, we see the loss of electrons, okay? We see that as the 3s, that 1 valence electron in the outer shell here is gone, all right? But they are now chemically stable, and they all have an electron configuration that's going to look like a noble gas. All of these gainers went towards argon, so each one of them have a new electron configuration that looks like argons. All of these up here went backward because they lost to the noble gas beforehand, which is neon, and that's totally normal and expected. So lastly, I do want to emphasize the reason you see none is because group 18, which has 8 valence electrons, unless it is helium, it has only 2, and group 14, 1 is stable. That's going to be your noble gases. Okay, they are already stable. They do not have an ionic electron configuration. Now they have a ground state electron configuration, and I wrote these here, the ground state electron configurations for these example elements, just to show the difference. However, in true form, these do not have ionic electron configurations because they do not become ions. All right, so that is what an ion is. Make sure that you have taken good notes, gotten this all down, and you got a mini quiz to take.